Welcome back. This is part B of week 4. We're diving into what is arguably the most important part of SQL, the data query language, or DQL. This is the select statement, and it's what you use most frequently when working with healthcare databases. Now, if data definition language, DDL, was about building the structure of our database, creating the tables, defining the columns, DQL, data query language, is about actually getting data out, getting the data out of the tables. This is where the real work happens. Generating patient lists, pulling lab results, creating reports for clinical dashboards, and answering the countless data questions that come up in healthcare operations. We'll be working with 3 main clauses today: select, where, and order by. Select, where, and order by. By the end of the session, you'll be able to write queries that retrieve exactly the data that you need, filter it based on specific conditions, and sort it in meaningful ways. Let me walk you through what you'll be able to do by the end of this session. First, you'll write select statements to retrieve specific columns from tables, not just grabbing everything, but being intentional about what data you pull. This matters a lot in healthcare, where we need to be careful about data exposure. Second, you'll use the where clause with various operators to filter your data. This is how you'll go from all patients to like female patients over 65 with Medicare insurance, the kind of specific queries you'll need in real clinical environments. Third, you'll learn pattern matching with like and I like. This is incredibly useful when working with medical codes like ICD-10 or LOINC, where you often need to find all codes that start with a certain prefix. Fourth, and this is a common stumbling block for beginners, you'll learn how to handle null values. Handle them correctly. Null behaves differently than you might expect, and getting this wrong can lead to missing data in your results. Fifthly, you'll combine conditions using and, or, and not to build complex filters. And finally, you'll sort your results using order by, including handling multiple columns and dealing with null values in your sort order. All of this will come together as you construct meaningful healthcare data queries using our xHealth database. So where does DQL fit in the SQL family? DQL, or the data query language, stands, as we said, for the data query language, and it really consists of just one statement: select. But don't let that simplicity fool you. Select is incredibly powerful and very flexible. The key to understand is that the data query language is read-only. When you run a select statement, you're not changing anything, any values in the database. You're just asking questions and getting answers back. This is fundamentally different from data definition language, which modifies structure, or the data manipulation language, DML, which we'll cover later, that actually modifies the data. So here's a reality check for you. In most database environments, the vast majority of operations are queries. Think about a clinical dashboard that refreshes every few minutes, or a patient lookup system that gets used hundreds of times a day. All of those are select statements running behind the scenes. The data query language, DQL, is also the foundation for reporting and analytics. Every clinical report, every quality measure, every calculation, every population health analysis starts with select statements, pulling in the right data. Now here's something important that trips people up. The order you write a query is not the order of the database execution. You write select first, then from, then where, and then order by. Again, I'll give you that order. We usually write select, from, where, and order by in that order. But the database actually processes it as a from first. It needs to know which table to look at. then the where to filter the rows, then select to choose columns, and finally order by to sort the results, put them in a specific order. So keep this execution order in your mind. It will help you understand why certain things work the way that they do. Let's look at this execution order side by side. On the left is how you write a query: select, from, where, and order by. But on the right is how it actually executes. Step 1 is the from. The database first identifies which table it's working with. It needs to know where the data lives before it can do anything else. Step 2, the where. Before selecting any columns, the database filters the rows. This is efficient because it reduces the amount of data that needs to be processed in the subsequent steps. Step 3, select. Now the database chooses which columns to include in the results. Notice this happens after filtering. The database has already narrowed down the rows. Step 4 is the order by. Finally, the results are sorted, and this happens last because you need to have the final data set before you can arrange it. So why does this matter? Understanding execution order helps you to write better queries and to debug problems. For example, you can't use a column alias from your select clause in your where clause because where is processed before select. I know that sounds very specific and some of you may not understand that, but it'll become clearer as we do some examples. All right, let's start with the basic select syntax. At its simplest, a select statement has two required parts: the select clause, which specifies which columns you want, and the from clause, which specifies which table to query. You list your columns after select, separated by commas. Then you specify the table name after from. And you end the statement with a semicolon. You need to remember that's important. All Postgres code statements have to end with a semicolon. And this tells the database that your statement is complete and you're ready to process. The select keyword is saying, give me these columns. The from keyword is saying, from this table. It reads almost like English. Select first name and last name from the patient's table. This is the foundation for everything else we learned today. It all builds upon this basic structure. Now, there's a shortcut you'll see frequently. Select star. That's select followed by an asterisk. And the asterisk is a wildcard that means all columns. So select star from patients returns every column in the table. When is this useful? Well, it's great for quick exploration when you're first looking at a table and want to see what's there. And it's also handy for debugging when you're trying to understand why a query isn't working exactly the way you thought it would. But here's my strong advice. Avoid using select star in production code. And there's several reasons for this. First, performance. If a table has 50 columns and you really only need 3 of them, you're retrieving data from 47 other columns that's unnecessary. That's wasted processing power and network bandwidth. Second, maintainability. When someone reads your query, select star doesn't tell them very much about what data you're actually processing. Listing specific columns makes your intentions much clearer. Third, and this is especially important in healthcare, select star might expose sensitive columns you didn't intend to retrieve. The patient's table might have social security numbers, or detailed addresses, or other protected health information. If you select star, all of that comes along for the ride. Being explicit about which columns you need is a form of data minimalization, which is a core principle of HIPAA compliance. Here's the better practice. Specify exactly which columns you need. In this example, we're selecting the first name, last name, date of birth, and insurance type from the patient's table. You can see that on the slide. The benefits are significant. Query execution is far faster because the database retrieves only the columns that you asked for. network traffic is drastically reduced, which matters if you're dealing with very large data sets or remote databases. Your intent is clearer. Anyone reading this query knows exactly what data it returns, and the code is easier to maintain because the dependencies are explicit. So try to get in the habit of listing your columns explicitly. It's a few extra keystrokes in writing your code, but it's worth it for the clarity and the safety that it provides. Sometimes the column names in your database aren't ideal for your output reports. Maybe they use underscores, or they're just abbreviated, or they just don't match what your report needs to show. And that's where column aliases come in. The as keyword lets you rename a column in your output. In this example, we're selecting first name, but displaying over the top of the column as, quote, first name, with a space in there. And we're selecting date of birth, but calling it DOB in the output. Notice the double quotes. That's important. In Postgres, if your alias has a space or any special character in it, you need to wrap it in double quotes. If it's a simple single word alias with no special characters, the quotes are optional, but it's easier to use the quotes routinely, and that way you won't make mistakes. Now, where do you use aliases? Reports that need human-friendly column headers that you might print out, or data exports where the receiving system expects specific column names, but really just for readability. When you're presenting query results to non-technical stakeholders, using alias is a benefit. One important note, the alias only affects the output. The underlying column name in your table is not altered. All right, let's look at our first xHealth example that we've been using. This query retrieves a list of active providers with their credentials and NPI numbers. Very simple code. We're selecting 5 columns: first name, last name, credential specialty, and NPI. The credential column might contain values like MD for medical doctor, DO, doctor osteopathy, nurse practitioner, or PA. Now, the NPI number is the National Provider Identification Number, and it's an industry standard. It's a 10-digit number that uniquely identifies healthcare providers in the United States healthcare system. Now, notice we have a where clause here. We're filtering to only show providers where is active equals true. We'll cover where in detail a little bit later, but this shows you how to combine the select and the where to get exactly the data that you want to display. This is the kind of query you might run to generate a provider directory or to verify a provider is still active in your system before scheduling a patient. Here's another useful example. Retrieving patient demographics. We're selecting patient ID, first name, last name, date of birth, gender, and insurance type. This is a very common query pattern for patient identification and insurance verification. Notice we're not selecting everything. We're not pulling addresses, phone numbers, or other fields that aren't needed for our report. The patient ID is our primary key, the unique identifier for each patient, for each row. Including this in your results is often important because names aren't unique. You might have multiple patients named John Smith, but each will have a different patient ID. One more select example. Pulling encounter summaries. An encounter, in healthcare terminology, is a visit or interaction, like an office visit, or a telehealth appointment, or an emergency room visit, and so on. So we're selecting the encounter ID, the patient ID, the encounter date, the encounter type, the chief complaint, and status. Now, the chief complaint is what the patient came in for, in their own words, their main concern or their symptoms. The status might be values like scheduled, in progress, completed, or canceled. This kind of query forms the basis of appointment lists, visit histories, and clinical workflow tools. You might run a version of this every morning to see what encounters are scheduled today. Now, let's move on to the where clause, which is where your queries really start to become powerful. Where lets you filter rows based on certain conditions. The syntax adds a where clause after your from clause, followed by the condition. The condition is evaluated for each row in a table, and only the rows where the condition is true are included in your output results. This is important. Where filters rows, not columns. Select chooses which columns appear in your output. Where chooses which rows appear. They work together, but do different things. And remember our execution order. Where is processed before select. The database filters first, then retrieves the columns you asked for. This is efficient because it means the database isn't retrieving column data for rows that will just be thrown away. To build conditions in your where clause, you need comparison operators. Let me walk through the main ones. The equal sign tests for equality, like gender equals F to return the rows where the gender column contains an F for females. Not equal can be written two ways. It doesn't matter which way you do it, they're equivalent. You can use the angle brackets like less than, greater than, adjacent, side by side, and that means not equal. Or you can use exclamation point equal, which means not equals. Both mean exactly the same thing. The status not equal to, quote, canceled returns all rows where the status is anything other than canceled. Less than and greater than work just as you expect. Like, for example, BMI greater than 30 returns row where the BMI exceeds 30. These work with numbers, dates, and even strings. Those string comparisons are alphabetical. Less than or equal and greater than or equal include the boundary value also. Like encounter date greater than or equal to January 1st, 2024 includes encounters on that date, not just after it. These are your building blocks. You'll combine them with the operators we'll cover shortly to build very sophisticated filters. Let's see these operators in action with our xHealth data. For our first example, we want to find the female patients. We select first name and last name from patients where gender equals F. Simple, direct, effective. A second example, let's find the completed encounters. We're looking for rows where status equals completed. This might be useful for billing purposes. You typically only bill for completed encounters. Another example, third, identifying patients with high BMIs. BMI over 30 is generally considered obese, which is a significant health indicator. This query, this third example, pulls encounters where the BMI is greater than 30. Notice we're querying the encounters table, not the patient table, because vitals, like the BMI, are recorded in the encounter table. When you need to check if a value falls within a certain range, the between operator is your friend. The context is where column between value 1 and value 2. In our example here, we're finding patients born between 1980 and 1990. The date of birth must be between January 1st, 1980 and December 31st, 1990. Another example here finds encounters in the first quarter of 2024 between January 1st and March 31st. Now here's the critical point. Between is inclusive. It includes both boundary values. So between 1 and 10 includes 1 and includes 10 and everything in between. This is important to remember, especially with dates, because you need to set your boundaries precisely. Between is particularly useful in healthcare for clinical ranges and date-specific queries. Let's look at this example. The first one finds patient with normal BMI. Normal BMI is considered 18.5 to 24.9. So we filter where BMI between 18.5 and 24.9. You might use this for population health reporting or to identify patients who don't need weight management interventions. Let's look at another example. It's a little bit of a workaround. We want working age patients, typically defined as 18 to 65. Since we store date of birth rather than age, we must calculate backwards. So for patients between 18 and 65 years old in 2024, we look for birth dates between 1959 and 2006. It's not perfect. It doesn't account for whether someone has or has not had their birthday yet this year, but it's a reasonable approximation for many simple use cases. Clinical ranges and date ranges like these come up constantly in healthcare retrieval work. Here's another powerful operator, the IN operator. It's essentially a shorthand for multiple ORs. Instead of writing insurance type equals Medicare or insurance type equals Medicaid, you can write insurance type in, and then you follow by a parenthesized list of the values that you want to retrieve. So in our example here, the first example finds patients with Medicare or Medicaid, the two main government insurance programs. The in clause makes this readable, even if you had 5 or 10 different insurance types to check for. All right, let's look at another example. The second example filters encounters to specific types: office visit, telehealth, or follow-up. Again, much cleaner than chaining together a long OR statement. Use in whenever you're checking if a column matches one of several possible values. It's more readable and less error-prone than a series of ORs, the OR chaining. Now we get to one of my favorite operators, the like. This enables pattern matching using wildcards, and it's incredibly useful in healthcare retrievals. The syntax is where, and then specify the column, like, followed by a pattern in single quotes. That has to be in single quotes. This is the rules of the syntax. The two wildcards you need to know are the % and the underscore. And we'll look at our examples to give you specifics. Now, the % matches any sequence of characters, including no characters at all. So J% matches anything that starts with a J. For example, John or Jane or Johnson or J, whatever. %SON matches anything ending with SON, like Johnson, Wilson, Anderson. %ANN% matches anything that contains ANN anywhere. So Anne, ANNE would give you a match. Joanna, Savannah, Annette, all of those would give a hit. The underscore matches exactly one character. So SM_TH matches Smith, Smythe, or Smath. The underscore is a placeholder for any single character. So let's look at the pattern table on the right here. Take a moment to understand each pattern and what will match. This will become second nature to you with practice. All right, let's see the like in action with some healthcare data. The first example, finding patients whose last name starts with S. We use the where, last name, like, S%. A simple pattern matching for name searches. The second example, finding patients with Gmail addresses. We use where, email, like, %@gmail.com, end quote. The % matches anything before the @ sign. Now here's where it gets really powerful for healthcare. The third example finds all ICD-10 codes for diabetes. The diabetes codes in ICD-10 are all E10 through E14. E10 is type 1, E11 is type 2, E13 is other specified diabetes, and so on. By listing where ICD-10 is like E1%, we're going to catch all the diabetes-related codes regardless of the specific subtype or category. So this pattern matching approach works brilliantly with medical coding systems. You could find all respiratory diagnoses with just using, quote, J%, end quote. All neoplasms with C% or D%, or all injury cases with the S% or T%. So understanding the structure of the coding systems makes your like queries much more useful, much more valuable. But there's one gotcha with like in Postgres. It's case sensitive. If you search for like Smith, and all lowercase, you won't find Smith with a capital S or all caps Smith. Postgres offers a solution called ILike, which is case insensitive. The syntax is identical, but ignores case differences. An example, where last name ILike Smith will match Smith, 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 any capitalization combination. This is much more practical for name searches where you can't rely on consistent data entry in the capitalization. An important note, ILike is Postgres SQL specific. Some other databases have different approaches to case insensitivity. In MySQL, like is case insensitive by default. In SQL Server from Oracle, you might use lower applied to the column before you do your like command, and that way it'll make everything in lowercase and eliminate the possibility of confusion. So you need to know your specific database application's behavior before you're doing your like or ILike. All right, now let's go into the null. And this is a topic where many beginners make lots of mistakes. Null in SQL represents the absence of a value, which means unknown or not applicable. But it's not a zero. It's not an empty string. It's not false. It's the lack of a value. So to find rows where a column has no value, you need to use, quote, is null. To find rows where a column has a value, you use is not null. In the examples, we're finding patients without email addresses and patients with email addresses. So here's the critical warning. Never use equals null or not equals null. I cannot stress this enough. Look at the red box on the side over there on the slide, where email equals null will always return 0 rows no matter how many null emails exist in your data. You're not looking for an equal to null. You're looking for email is null. Sounds like splitting hairs, but it's very important that you understand to be able to get the reports that you're trying to publish. Null represents an unknown, and you can't test if an unknown value equals another unknown value. The result of any comparison with null is not true or false. It's null, which is treated as not true in a where clause. So this trumps even experienced programmers at times, especially coming from other languages. So burn this into your memory. Is null, not equals null. Null values are extremely common in healthcare data, and handling them correctly is essential. First example, let's find active medications. A medication without an end date, where end date is null, is typically still active. Combined with checking that is active is true, this query finds current medications for patients. Another example, finding encounters with missing vital signs. If blood pressure systolic is null, that's a gap in documentation. You might use this for quality assurance, identifying encounters where vitals weren't recorded. Here's a third example, finding patients who need insurance updates. If insurance type is null, we don't have insurance information on file for that patient. This could affect billing and eligibility verification. So the point is that null isn't just a technical curiosity. It has very real meaning, especially in healthcare workflows. Missing data needs to be identified and frequently addressed. Now, let's combine conditions using logical operators and, or, and not. And requires both conditions to be true. In the first example on the slide, we're finding patients who are female and have Medicare. Both must be true for a row to be included, to be selected. Or requires at least one condition to be true. The second example finds patients with Medicare or Medicaid. Either one qualifies the row for inclusion. How about not? Not negates condition. The third example finds patients where insurance is not self-pay, essentially excluding self-pay patients. These operators let you build complex multi-condition filters, but there's a catch, which brings us to the next issue. When you mix and or in the same where clause, operator precedence becomes critical. And is evaluated before the or, just like multiplication before addition in math clauses. If you look at the wrong example in red on the slide there, where gender equals F and insurance type equals Medicare or insurance type equals Medicaid, so what's going to happen? Look at it carefully. You can figure it out. Because and is evaluated first, this is interpreted as a female and Medicaid, or Medicaid. So you're going to get all the female Medicare patients and all the patients that have Medicaid, regardless of their gender. And that's probably not what was intended. So the correct version uses parentheses to make the grouping more explicit. So in this example, we say where gender equals F and insurance type equals Medicare or insurance type equals Medicaid. Now it's clear. Female and either Medicare or Medicaid. The alternative is to use that in clause that we talked about earlier. It's even cleaner, where gender equals F and insurance type in, and put the two strings, Medicare and Medicaid, in parentheses. My advice to you is whenever you mix and or, use parentheses to make your intent explicit, even if they're technically not required, and that makes your query easier to read and less prone to logical errors. All right, we've covered how to select columns and filter the rows. Now let's sort our results with order by. Order by comes at the end of your query, after the where clause, if you have one. You specify which column or columns to sort by, and optionally whether to sort ascending or descending. ASC means ascending order, A to Z for text, or smallest to largest for numbers, earliest to latest for dates. This is the default. If you don't specify, you will automatically get ascending. Now, DESC means descending. You go going from Z down to A, or largest to smallest, or latest to earliest. Remember our execution order. Order by is processed last. The database identifies a table, filters the rows that you're going to select, selects the columns you specified, and only then sorts the results. This makes sense because you need the final data set before you can consider arranging it. Or let's look at some single column sorting examples. First, alphabetizing patients by last name. So order by last name. ASC gives you Adams before Baker before Chen. Since ASC is the default, you could also just write order by last name. All right, second example, showing most recent encounters first. Order by encounter date descending. Puts the newest encounters at the top. And this is typically what you want for a visit history, the most recent first. Let's look at the third example. Ranking patients by BMI from highest to lowest. We're selecting from encounters where BMI is not null, filtering out the rows with missing BMI data, and then order by BMI descending. The patients with the highest BMI will therefore appear first. Notice in this third example, it combines the where and order by, and that's completely normal. That's very common. You filter to the rows that you want, and then you sort the rows for your report. You can sort by multiple columns, and this is often necessary to get meaningful results. For example, sorting patients by last name, then by first name within each last name. And this is how you'd expect a patient directory to be sorted. All the Smiths are together, and within the Smiths you have Alice before Bob before Charlie. A second example, sorting by insurance type, then by last name within each insurance type. You might use this to generate patient lists organized by the payers. The key is left to right priority. The first column is your primary sort. The second column only matters when the first column has ties. Think of it as sort by this, and if there are ties, break them by that. You can mix ascending and descending in multi-column sorts. So if you say order by encounter date descending, last name ascending would show the most recent encounters first, and within the encounters on the same date to sort them alphabetically by name. Here's a nuance that comes up with real-world data. How are null values sorted? Postgres' default behavior is that with ascending sort, nulls come last. With descending sorts, nulls come first. This is because null is considered unknown. The database doesn't know where to put it, so it goes to the end or beginning depending on your sort direction. But you can override this with nulls first or nulls last specifically specified in your query. The first example sorts medications by the end date ascending but puts nulls first. This means active medications, those without an end date, appear at the top of the list. Let's look at another example. The second example here sorts end date descending, puts the nulls last. Recent end dates come first, and medications without end dates come at the very end. So this level of control is important. When null has meaning, active medications with no end date shouldn't necessarily be sorted from the bottom. They might be exactly what you want to see first. All right, let's see order by in a realistic healthcare scenario. First, recent diagnoses first. When reviewing a patient's diagnosis history, you typically want to see the most recent issues at the top. So we're going to order by diagnosed date, descending. This accomplishes this. Second, another example, let's look at the highest claims first. For financial analysis or identifying high-cost cases, sorting insurance claims by billed amount, descending, puts the biggest claims at the top. Another example, lab results by test date, then test name. This gives you a chronological view with the most recent tests first, and within each test, and within each date, the tests are alphabetized for easy scanning. The two-column sort makes the results much more usable than sorting by just a single field. All right, let's put everything together with some complete query examples. These demonstrate how select, where, and order by work in conjunction with each other. The first query, this query finds diabetic patients ordered by diagnosis date. We're selecting patient names along with diagnosis details from multiple tables. The where clause uses like to find that ICD-10 code that starts with the 11, which is type 2 diabetes. We're also filtering for chronic conditions. The order by puts the most recently diagnosed patients first, which might be useful for identifying new cases that need care management outreach. One note, this query uses a simplified multi-table syntax that I'll call implicit joins. You'll notice that we list multiple tables in the from clause separated by commas. This works, but in week 5 we'll cover the proper way to do joins. So when we're using multiple tables, it's a little clearer and a little more flexible. But for right now, just understand that we can query data from multiple related tables without further specification. Here's a complete example query. This query finds active medications. It combines concepts we've covered. We're selecting medication name, dosage, frequency, and the start date. The where clause has 2 conditions joined by and. Is active, must be true, and the end date must be null. Both conditions indicate the medication is currently being taken. The order by shows most recently started medications first, which is useful for medication reconciliation or understanding what was most recently prescribed. This query demonstrates using a Boolean field, is active, null, checking end date is null, and database sorting all in one great example. Our final complete example, finding abnormal lab results. The select here includes test details, name, value, unit, reference range, abnormal flag, and the test date. This gives you everything you need to know to review the abnormal result. The where clause uses in to check for multiple abnormal flag values. In healthcare systems, H typically means high, L means low, and A means abnormal for non-numeric tests. We're also filtering to tests from 2024 or later using a date comparison. So the order by uses 2 columns. The test date, descending, puts the recent tests first, and test name, ascending, alphabetizes the tests. This is exactly the kind of query that might power an alert system or a provider's inbox, surfacing the lab results that need urgent attention. So let me reinforce the execution order one more time with this visual here. When you write a query to find Medicare patients sorted by last name, here's what the database really does. In step 1, it executes the from. It identifies that we're working with the patients table. This is the data source. Step 2, the where. It scans through the rows and keeps only those where the insurance type equals Medicare. Non-Medicare patients are filtered out. Step 3, the select. From the filtered rows, it extracts just the columns you asked for. First name, last name, date of birth. Other columns are not included. Step 4, the order by. The resulting rows are sorted by last name in ascending order. The final output is a sorted list of Medicare patients with just the 3 columns you requested. Understanding this flow helps you write efficient queries and debug problems when the results aren't exactly what you expected. All right, so let's recap the 6 points from today's lesson. 1. The select retrieves specific columns. Avoid select star in production code. Be intentional about which data you want to retrieve. 2. Where filters rows using conditions. It's processed before select, making filtering efficient. 3. You have a rich set of operators available. Equal, comparison, between, in lists, and like, all for powerful matching. 4th, null handling. Null handling requires special syntax. Always use is null or is not null. Never say equals null. That doesn't work. 5, and, or, and not let you combine conditions, but use parentheses to make your logic explicit and avoid precedence surprises. And finally, 6th, order by sorts your results. Like with ascending or descending for reverse order, you can sort by multiple columns. These fundamentals will serve you throughout this course and your career in health informatics. In Part C, the third part of this week's lesson, we're going to shift gears from SQL to Health Information Standards. We'll explore why interoperability matters and how different standards have evolved to address it. We'll cover the history of Health Level 7, going all the way back to 1987 when healthcare organizations first started trying to get their systems to talk to each other. We'll look at HL7 version 2, which is still the most widely deployed healthcare messaging standard, despite it being several decades old. And then we'll explore HL7 FHIR, the Fast Healthcare Interoperability Resources, which represent the modern API-based approach to healthcare data exchange. And we'll also touch on OpenEHR and its unique two-level modeling approach, an international standard. And finally, we'll examine the U.S. regulatory landscape using the 21st Century Cures Act and the U.S. CDI, which are driving interoperability requirements for healthcare information technology systems. It's going to be a lot of ground to cover, but it's essential context for understanding how healthcare data moves between systems and why database skills that you're learning matter in the big picture. Look forward to seeing you in Part C.